Good afternoon, everybody, and welcome to another RUS Copernicus webinar. My name is Miguel Castro Gomez, and I work as remote sensing specialist for Cerco Italia in the RUS Copernicus project. Today, I will be your host for this session, in which we will address the topic of processing Sentinel-2 data using the R programming language. So before starting, I would like to share with you the outline for this session. So the first thing I want to introduce you is to the RUS Copernicus service, the project that is hosting this series of webinars and with which you might be already familiar with. Next, I will briefly talk about the technical aspects of the Sentinel-2 mission to make sure we are all on the same page and that we get the same knowledge about the data we are going to be using in the third point of this session, which is going to be the exercise. For that, I will be using a RUS Copernicus virtual machine to run the code and to explain it to you. At the very end, we will dedicate some time for a Q&A session. To make sure we can answer to all your questions, I would recommend you to send your questions as soon as possible. Do not wait until the Q&A session because we might not have enough time, so make sure you send your questions as soon as you have them. And as always with other RUS Copernicus webinars, it is being recorded and it will be available in our YouTube channel and in our RUS training website. I will give you more information about that later. Okay, so let's get started, and for that let's have a look to the RUS Copernicus service. Let me give you a brief introduction to it. Well, first of all, RUS stands for Research and User Support for Sentinel core products. It is an initiative founded by the European Commission and managed by the European Space Agency, with the objective to promote the uptake of Copernicus Sentinel data and support R&D activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed in virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. So what does that mean in other words? Well, with the large amount of data produced by the Copernicus program, the challenge in Earth observation with Copernicus data is no longer data availability, but rather storage and processing capacity. To solve that, RUS Copernicus offers virtual machines so that you have the appropriate computing environment to handle the data. In addition to all that, RUS also provides a specialized user help desk to support your remote sensing activities with Sentinel data, and a dedicated training program that includes webinars like the one of today, but also face-to-face events that we do throughout the year. So some updates regarding the RUS Copernicus project. Since last September 2020, RUS Copernicus has designed a new offer in order to reach a greater number of users and provide them with RUS tools and services. As before, we organize the RUS offer around two main activities. First, the support to individual users and their R&D projects, and secondly, our well-known training activities, which include face-to-face events, webinars, and support to external trainings. So let me comment the main changes in each category. Regarding face-to-face events, not much has changed. We maintain a small audience to ensure a high level of interaction. VMs, in this case, will have 4 or 8 cores depending on the processing needs of the exercise, and will last 1 month maximum, period in which the ICT support will also be available. Regarding webinars, we will maintain the rate of 1 webinar per month, and we will keep publishing the step-by-step guides as before. The update here is that there will be a limited amount of VMs for webinar repeat, and their duration will be 2 weeks maximum. Next, the support to external training organization and operation. We will maintain this activity, but there will be a limit in the number of VMs available, which will also have the ICT support. And finally, the last update regarding the support we provide to individual users. In this case, the VMs will no longer be available for this category. We will provide a Docker image to make the RUS working environment available. This will include a suite of pre-installed open source tools for processing Copernicus data. Support will be available to help users setting their Docker containers in their local PC in case they are not familiar with the container technology or with Docker. And finally, and for your information, RUS VMs are provided from Copernicus DS and other cloud providers. So Let's move on to the RUS websites, where you can find all the details. The first one, rus-copernicus.eu, contains all the information about the project, and it is here where you can register for the service and access your virtual machine. The second one contains all the information about the training activities we organize, such as this webinar. So rus-training.eu. If you want to stay updated with upcoming training activities, I recommend you to check the website from time to time. Finally, and as I said at the beginning of this webinar, we also have our YouTube channel called RUS Copernicus Training, where you can find all our previous recorded webinars. So I recommend you to have a look later on after this webinar. I'm sure you can find topics of your interest. We already have a very long list where we cover many applications using Copernicus data, using not only Sentinel-2, but also Sentinel-1, Sentinel-3, and Sentinel-5P, which are the Sentinel missions that are, as of today, up and running. Okay, so let's move on our presentation, and now we are going to focus on the Sentinel-2 mission. So I want to share with you some basic information about this satellite. I'm sure most of you are already familiar with it, but just some key information for those of you that might be new to this data. So the Sentinel-2 mission, first of all, is formed by two twin satellites known as Sentinel-2A and Sentinel-2B. They are faced at each other at 180 degrees. Together with its wide swath of 290 kilometers, it delivers a very high visit time, which is of 5 days at the equator with the two satellites. Of course, if you go northern or southern in latitude, this revisit time will decrease. The satellites have a multispectral high-resolution instrument with 13 spectral bands. And a note on these bands, their spatial resolution changes. So 4 bands in the red, green, blue and near-infrared are provided at 10 meters pixel size. Those are band 2, 3, 4 and 8. Then we have 6 bands which are located in the red edge and in the shortwave infrared, which are provided at 20 meters pixel size. And finally we have 3 bands which are used for atmospheric correction and are provided at 60 meters. A small note here on the different products that are available from the Sentinel-2 mission. You can find mainly the level 1C and the level 2A. Those are the levels available to users. The level 1C provides reflectance values at the top of the atmosphere, while the level 2A provides reflectance values at the bottom of the atmosphere. So level 2A has already gone through an atmospheric correction using the Sentinel algorithm. And these products, the ones with an atmospheric correction, are produced and delivered systematically by ESA. So something to take into account, and I think a good detail. Okay, so that's all for my introduction about the Sentinel-2 mission. Of course, you can find more information on the official website of Sentinel-2, and I do recommend you to have a look if you are not familiar with the satellite yet. Okay, so let's get started with the exercise. So what is going to be the objective of our analysis today? Well, what we want to do is to plot an NDVI time series in a region of interest located in the United States, more in particular in California, by deriving the vegetation index, so NDVI, from Sentinel-2 products using the R programming language. So in this exercise, I wanted to add the temporal dimension by deriving this time series, since I think it's one of the key components of the Copernicus program. If you remember from the introduction I just gave about the Sentinel-2 satellite, one of the characteristics is that you have 5 days revisit time with the two satellites, Sentinel-2A and B, at the equator. However, the northern you go or the southern you go in latitude, the revisit time is gonna decrease. So you will get a lot of products over your region of interest. And whenever you start working with the Copernicus program in general, or in particular with Sentinel-2, you will see that you have a huge amount of data over your specific location. So the temporal component of the analysis when working with Copernicus is one of the things you will face for sure if you start to do such work. So in this exercise, I don't want to focus the final result in something very advanced, but rather keep it simple and easy, touching one of the key components of Copernicus, which is the temporal dimension, to make sure that both people with experience in R that is attending this webinar, but also beginners, can follow, can understand the logic behind the use of R for processing satellite data, in this case optical data from the Sentinel-2 mission, and so on. So what are the tools we are going to use, or I'm going to use in this exercise? Well, we will be working within one of the components of the RUS Copernicus program, which are the virtual machines. Within that virtual machine, I will be using an R script that has already been written, that I have already created, and that will be available for those of you repeating this exercise. And I will be using the Jupyter notebook, or actually the Jupyter lab, to run my R code. If you are not familiar with what is Jupyter notebook or Jupyter lab, I will talk a little bit more later on once we start the exercise. But so far, let me go to the RUS Copernicus VM and let's start the exercise. Okay, so here I am in the welcome page of the RUS Copernicus VM, and as you can see, we are accessing this environment which is sitting on the cloud via a web browser, in this case Google Chrome. So I'm just gonna go full screen here to have a better visualization first of all. And now with the credentials inserted, I'm just gonna log in. Okay, so here we are in the RUS Copernicus VM, and let me give you a brief introduction to it in case this is the first time you see it or the first time you work with a virtual machine like this one. Well, as I said during my introduction, RUS Copernicus VMs come already pre-configured and with a list of predefined software installed. So for example, we can see here we have Snap, which is the dedicated software of ESA to analyze Copernicus data. We also have QGIS, we also have RStudio, for example, to run our code, Jupyter Notebook, etc. So as you can see, the machine comes ready to use, so you can start your EO projects straight ahead. For those of you that are new to virtual machines, I think this is one of the easiest and most friendly steps you can make when you start working with cloud computing. Basically because a virtual machine will give you an interaction or to the user, to yourself, that is very similar to what you can find in your regular or personal laptop. So for example, we have a terminal window to interact via command line with the VM. We have the file manager system where we can put our files, etc. We also have a dedicated internet browser within the virtual machine, and so on. So as you can see, everything you can expect from a computer, you can find it within the VM. The main difference here is that we are being backed up by cloud resources, so that we can have the appropriate environment to handle and process our task, in this case, the analysis of satellite imagery. So the first thing I want to show you in this exercise is how to access Copernicus data. Some of you might already be familiar with that, but I think it's important to cover it in case some of you are new to Sentinel-2 or to Copernicus in general and don't know where to find the data. Remember, Copernicus data is free and open for everybody, so the only thing you need is an account. The next thing you need to do is to go to sci-hub or sci-hub.copernicus.eu and in here access the Open Hub. Once you are here, and again, once you are registered, you just need to log in and you access this interface where you can set the search parameters that you want. So for example, by opening the advanced parameters panel, we can first of all select the sensing period we are interested on. So let's say, for example, from the 1st of November until the 15th of November. And then we can select, for example, the Sentinel mission we are interested on. In this case, let's pick Sentinel-2 since this is the data we're going to be using for today. We can specify the specific satellite that we want, either Sentinel-2A or B. If you don't want to make this difference, you can just leave it empty and it will select both. You can then select the product type. So remember, level 1C, it's top of the atmosphere reflectance, and level 2A is bottom of the atmosphere reflectance. In our case, I'm going to pick level 2A. And finally, you can set a threshold for your cloud cover in case you want to apply that. So once you have your advanced search parameters, it's just a matter of drawing your region of interest on the map. So let's pick, for example, the study area of today, which is in South California. So it's very close to the border with Mexico and basically here. So once you are in your region, you can just change to the drawing mode, and now you can just draw your polygon that represents your region of interest. Once you have all of this, you can click on the icon here, search, and in a few seconds you will get the list of products that match your search. In this case we got 3 products, and you can see here on the left side this list, this panel that pops up with the results and a preview of the images. So if you want to access more details about the specific or a particular product, you can click on the eye icon here, and you will see more details about the product. Something relevant, for example, is the true color pre-visualization that you can see. I think this is very helpful, especially if you care about the clouds, which with optical data is always a concern. But together with this, you can also access metadata about the product, which you can basically explore here. Once you have identified a product of interest, you can just click on the arrow here, which will start the download process. And remember, in this case, we are using the internet connection and the storage capacity of this specific virtual machine. As you can see, it is quite fast, the download, and in a few seconds you will get the product in your virtual machine ready to be analyzed. So for today's exercise, I have pre-downloaded the products we are going to be using, so I will not download all of them. Just to let you know, I have taken several products throughout the year of 2020 to see the temporal evolution of NDVI at specific locations located in this product. So let's get to the next point I want to explain you. So as I said while I was introducing the exercise, today we are going to be using Jupyter Notebook to run our R script. More in particular, I'm going to be using the R installation that comes by default with the Anaconda distribution. Anaconda is an open distribution of the Python and R programming language that not only gives you access to these programming languages, but also to some tools, to some package management that helps you to create virtual environments or Conda environments to handle different versions of modules and packages, and some dependency management, etc. So it's just a distribution of Python and R with some extra tools to handle and manage that installation. So Anaconda is part of the list of softwares that is available and pre-installed in the RUS virtual machine, and I'm just going to make use of that. So the first thing I need to do is to basically activate my Conda environment, and this I can do by just writing the command conda activate followed by the name of the environment that I have created in advance and that contains all the dependencies I need, all the R packages, and also Jupyter Lab in this case. So by writing this and clicking enter, I now get the confirmation that I have activated this environment, and I can see it here, and now I can just launch Jupyter Lab. So what is Jupyter Lab, or what is Jupyter Notebook? Let's say. Well, the Jupyter Notebook is a web-based application that allows you to combine your code, in this case Python or R, together with rich text elements like images, paragraphs, hyperlinks, etc. So for example, this Jupyter Lab environment gives me the possibility to write my text with hyperlinks, images, etc. and together I can write some code. So the whole idea of Jupyter is to create a framework where you can share your code in an easier way. So you can share it with others, and obviously it's going to be easier for them to understand the logic behind your analysis if you combine your R code together with some explanations or some context like the text you can find here. So I think this is something helpful, especially in the context of this webinar. That's why I have chosen it instead of RStudio. But obviously you can just take this code and run it in RStudio. It's just gonna run the same. So let me go full screen here so that we get a better visualization and we can start the exercise. So as you know, we are going to be running this temporal series of NDVI over, in this case, the Imperial Valley in the USA. So the way I have structured I just want to show you now the way I have structured the exercise. So basically, and if you are repeating this exercise, you will find this text here that is introducing you to the problem, to the Copernicus program, and I'm also leaving you here a reference for the technical implementation of Sentinel-2. So if you're interested on this, I will recommend you to read it. I will not do it since it's basically the same as I have explained in my presentation a few minutes ago, so we can just skip that part. I'm also leaving you some links and references to some R tutorial that I think are nice to follow, and also to the Jupyter Notebook documentation and tutorials in case you are not aware of Jupyter Lab or Jupyter Notebook. I think it can be helpful for you if you're new to this. So how are we going to proceed? Well, the first thing we will do for this analysis is to load some R packages. I will briefly comment the ones we are using and give you a little bit of context of why I have chosen them. Then we will load some auxiliary data, so some files that we need to perform our analysis. We will then load the Sentinel-2 products that we will be using today into the R session or into the R kernel in Jupyter Lab. And then once we have the data loaded, we will start to do some processing. In this case, as you can see, rather simple. We will do a subset. Once this is done, we will derive NDVI. We will extract the NDVI values at specific pixel locations. And finally, we will just plot the evolution of this, which is basically the temporal series. So let's get started, and the first thing we're going to do is to load the R packages. Before that, I want to point out the fact that in Jupyter Lab you have basically two types of cells. One, the most important one are the code cells. So basically you can identify them because they have this kind of gray background color. Also, for example, because when you click on them, you can see here it's written code, and well, basically because it's here where we write the script, in this case R or Python if you are working with Python. In opposition to code cells, you can find markdown cells, which is basically this kind of cell where you can write the rich text elements that can be added to your code for better understanding. So basically this is a cell that follows the markdown structure, and whenever you execute it, then it renders the output, and you can read it easier. So now comes the question of how to run the code or how to execute the cell. Well, there are different alternatives in Jupyter Lab, and I'm leaving you here a note on that. But basically the first thing you need to do is to select the cell that you want to run, and you do so by just clicking somewhere on the cell. And once you do so, you can, for example, click on the play button here or the run button. You can also go to the run tab and select one of those options. But I think the most convenient option is to just press Ctrl Enter or Shift Enter. Whenever a cell gets executed, you will see that this little white dot becomes dark. It means that the kernel is busy, so it's executing the code. And here an asterisk will show up. Whenever that asterisk becomes a number, it means that the cell has been executed, and that number will be the index of the cell. So for example, here we will get a number 1, in the following we will get a number 2, and so on. In that way you can keep track of the order you have followed in your execution. Okay, so point number 1, load R packages. So which packages are we going to use? As you know, R comes with several tools, several packages by default. However, most of the times you will need to download, install, and activate other R packages that contain the tools, the algorithms for a specific application, for specific analysis. So in our case, for this Sentinel-2 data processing, we need some extra packages that I have already pre-installed and that I'm only loading here in this R session. And you can see here the list. So if you're familiar with R, I'm sure you recognize them. For those of you that are new, I think it's helpful if I give you a brief description of them. So tidyr is basically a very well-known package in R that will help us to reorganize our data. It's, let's say, a data management package The RGDAL package gives us access from R to the GDAL library, which is extremely well known in satellite data processing or geospatial analysis. ggplot2 is going to be a library to create some visualizations, some graphics. Raster, I would say, is a mandatory, almost mandatory package in R to process raster data, so the name is very descriptive. Leaflet is just an R version or an R adaptation of the Leaflet module of JavaScript, which will allow us to create interactive maps. RasterViz, GridExtra, and RColorBrewer are again packages that we need for raster data manipulation and visualization. And finally, Plotly is also an R version of the Plotly library in Python, which is mainly used for interactive visualization as well. Okay, so basically those are the tools we are going to use, and I have created here a list in R, so you can see it's called PCK, and this variable I'm going to pass it to this function here to load the packages. So some comments in R, especially if you are coming from Python and you are new to R, or maybe if you're completely new to both Python and R. I'm gonna use this icon here, this arrow followed by this dash, to assign values to a specific variable. So on the left side you will see the name of the variable, and on the right side whatever is happening. So I'm creating this list, or well, this vector of names containing the names of the R packages that we are going to use, and then basically I'm saying to the R kernel, look for these packages in my installation, and if they are not present, install them. Since they are already installed, this will be skipped, and it will only be they will only be activated. To activate them, I will use the supply function in R. The supply function is a function in R from the family of the apply functions, and you can find, for example, alternatives to these, like the lapply function or mapply. Basically, those are functions in R that allow you to pass a list as input, and then you can pass a specific function that you want to apply to the elements of this list, and it will give you back an output following the same order. So it's a very handy tool in R that you definitely should check out. So basically I'm saying use this variable PCK, which contains the list of packages I want to use, and to each of these elements apply the function require. Require, or library in R, is the function we need to activate a specific module. It's like in Python you use import followed by the name of the module. In this case it's require. Okay, once we do so, the next thing we will do is to set our working directory, something also very common and very advisable when working in R in particular, which is setting the folder of reference for this specific project. So you can see this is the folder I have set. It's a folder that is located in my virtual machine. So if I just go to my file manager system, you can find it here. It's basically folders with the data. So in the original folder you can see, for example, the list of products. Actually, now that I'm here, I want to point out that, as you can see, the Sentinel products, the Sentinel-2 products we're going to use in this exercise are in the .safe format. Basically what I have done is that I have downloaded them in advance and I have unzipped them. I do this because when working with R, it's better to have the products unzipped so that I can navigate through the different subfolders and do my work. So this is just an advice I would give you, but definitely this is something you can also automatize in your R scripts. Okay, so let me just go back to full screen and run the first cell. And now the output comes, so we just get some prints, some messages from the different packages, and basically at the very end we get the output of the supply function. So basically it is confirming us that all the packages have been loaded with this true value. So true meaning that yes, the package is installed and it is active and ready to use. If you are repeating this exercise, or if you are loading your packages for other projects and you see a false here, that would mean that that specific package was not loaded, it's not active, and basically you would see also an error here. So if you rerun this cell, basically you can just get rid of this printing, and you get directly the output of supply. Okay, so we got our packages activated, so now we can start with the next step, which is load auxiliary data. So in this case, what we are going to do is load our shapefiles that we will need for our analysis. The first one is going to be the study area. So it's a shapefile I have created in advance that represents, as the name indicates, the region of interest. And then I'm going to load another shapefile, in this case points, that I'm going to call points_SA, and those are the points, the coordinates that are going to identify the pixels that I will use as reference to extract the NDVI value later on and plot my temporal series. To load shapefiles into the R session, there are different alternatives in R. One of the very well known is to use the read OGR function, which is the one I'm using here. The next thing I'm going to do is to plot the study area so that we can locate it on a map. And for that I will be using the leaflet library, or the leaflet package, to plot an interactive map in R, and at the same time I'm going to specify a specific tile, so a specific background that I want to provide. And this is something you can customize, and you can find on the internet a lot of information about it. And once I have this tile, this background map, I'm going to add a polygon, which is going to represent my study area. So as you can see, I have here another variable called study area number 2 that I'm using as the variable in the interactive map here. The reason for this is that the leaflet package works with special elements that are projected into the WGS84 projection, so in lat/long coordinates. However, my original study area shapefile is projected in UTM, and the reason for this is that when working with Copernicus data and other layers like shapefile, you want, as always, when working with geospatial information, you want them to have the same CRS, the same coordinate reference system. By default, Sentinel-2 data is projected, as I said, in UTM. So whenever you create something to represent your study area, for example, make sure you project it in the same CRS. Since I want to also represent my study area in a leaflet map, I just need to reproject it or to transform it into lat/long coordinates, and I do so by using the SP_transform function. So I just pass the original study area variable as input, and I specify that I want a CRS in lat/long following this specific datum. Okay, so once this is done, I'm just telling R that I want to visualize the M variable, in this case the leaflet map. So let's run this and have a look. Okay, so the first thing we get is this print of the shapefile. So this is basically the outputs of these two functions here. So what you can see is that R, as any other programming language, doesn't give you a graphical visualization of your files that you have loaded directly. This is normal and expected. But this specific function, read OGR, gives you key information about the data set that you have just loaded into the session. First of all, we see it is a shapefile, so that's good, we know, but it's just a confirmation. We get its source, so from where in my virtual machine this specific file is coming. And if you pay attention, when we were loading it, we didn't specify the folder where it was. And we didn't do so because we already set the working directory in advance. So by default, R is going to go to our working directory and it's going to try to find the file of need. So we get here the path, and we also get key information, which is the number of features and the number of fields. So if you remember from a shapefile or from vector data, let's say we get its attribute table, and each attribute table will have a specific, let's say, column, a specific attribute, and a number of entries for that specific attribute, right? So the study area has one feature, one field, so one polygon and one attribute, which is going to be the ID. For the other one, which is the points, we get 4 features and 2 fields. So 4 features meaning 4 points, and 2 fields meaning 2 columns in our attribute table. So as you can see, by just loading the data, we can get a lot of information about the, in this case, a shapefile, just by reading the metadata information that it's printed. Okay, and just below we can see the interactive map that we have open here in Jupyter. So we can basically locate our study area, and as you can see, this is well, I told you it's in the United States, in California, very close with the border of Mexico. We can just find the Imperial Valley. It's an irrigated, well, it's an area that's irrigated for agriculture, and I think it's gonna just work fine for our study case today. Well, one of the advantages, I would say, or one of the nice features of working in Jupyter Notebook is you can, create these interactive maps that I think make the understanding of the analysis much easier. Obviously, in RStudio, you can also create interactive maps. I'm not saying it's not possible, but I think the integration of everything, I would say, in Jupyter Lab or Jupyter Notebook, it's a little bit more friendly, but definitely this is a personal opinion. Okay, so let's go to the next point number 3, which is load Sentinel data. So what we are going to do now is ingest the products that we have into the R session, into the R kernel, so that we can work with them. So the first thing we are doing is setting a specific folder where the data is stored in our virtual machine. And as you can see, this is located in shared training R01 Sentinel-2 processing original. So this is the specific folder I just showed you before. And what we are going to do is create this variable S2. Once this is done, we are going to overwrite this variable with a new command, and basically we are going to create a list. So we are specifying this by using the list function of R, and I'm saying, okay, let's go to this specific path. So the S2 variable at this point is pointing to this path, and we are saying go to this specific folder, go into the different subfolders that you can find, and look for files that follow a specific pattern. And that pattern is specified here in this argument, which is B0, then followed by 2, 3, 4, or 8. And this is what these brackets mean. So we're just passing this variation of the sequence after the 0. And then underscore 10m.jpg, GP2. So that's basically what we are saying, and once we do so, or once we create this list, what we are going to do is again use the family, the apply functions in R. So this family of functions like apply, supply that I talked before, and we are going to say, okay, the input is going to be this list of files, this list of absolute paths to my Sentinel-2 products, and I want to apply to each element of the list a specific function to load the file into R, and that function is going to be the raster function. So raster is a function from the raster package that allows you to load a raster file into R. And once this is done, everything will be saved, again overwriting the variable S2 in S2, and finally we will just have a look. So let's run this and let's see what happens. Well, it's done. We are now visualizing the output of so the first element of S2. And remember, since we are using l'apply, what we are getting back is a list. So the structure, let's say the data type is a list. That's why we can use square brackets to specify an index for the list. So for example, since this is a list, I can just write head and visualize the top part of this specific list. And we get back the first 6 elements. This is just pure R programming, right? If I write tail, for example, I get the bottom part of the list. And again, if we use a specific index with square brackets, we can access an element. So what can we see here? What's the output of this raster function? Well, first of all, it's telling us that the file has been loaded as a raster layer. So its class is raster layer. It's giving us some metadata information that is very important. For example, the dimensions. So in this case, the number of rows, the number of columns, and their multiplication, which is of course the number of cells. We get the resolution 10 and 10. And now the question is 10 by 10 what? Well, we know in advance, since we know the characteristics of Sentinel-2, that this refers to meters. However, there's something here to point out. R is going to use the units that are specified in your coordinate reference system. So if we go to the CRS attribute here, we get the projection of the data, so UTM, zone 11, the datum that is being used, and there's one specific parameter that it's called units. Most of the times when working with, let's say, standard CRS, the units are going to be meters, but definitely this is something you need to know in case it's different for your work. So this 10 by 10 in R refers to whatever units is defined in your projection, in this case meters, which obviously matches the specification of Sentinel-2, which is 10 by 10, so no surprise there. Okay, we get the source of this specific raster layer. So what are we looking at? Well, we are looking at the band number 4 from a product that was loaded from this specific folder. So well, and it's underscore 10 meters.jpg. So something maybe you don't know, or maybe yes, is that the Sentinel-2 products follow a specific naming convention, meaning that the name of the product here is not randomly generated, it follows a structure. And the thing I want to point out is that part of the name contains the sensing time. So it is here, Sentinel-2 satellite A, multispectral imager level 2A, so bottom of the atmosphere reflectance. Then this is followed by the year of the sensing time, so 2020, in this case 05 for the month and 05 for the day. This is followed by this fixed character, which is just a T, and then we can get the hour of the acquisition, so 18 hours, 19 minutes, 21 seconds. And well, then you can see all the numbers that are not very relevant. And the last one I want to point out is this one here. In this position, you will always find the tile of this product. The tile, when the Sentinel-2 products are acquired, they all follow, let's say, a tile division. And this specific product belongs to the tile 11 SPS. And this is information that you can use to later on look for products from the same area. So this is a product from May. For example, if I open the first one, we can see that it's also from May because it's the band number 2. But for example, if we open the number 6, now we get a product from June, and so on. Okay, so now we have our products ingested in R, and they are stored in this S2 variable, which by the way has a length. We can check that by using the length function in R. So this list has a length of 24 raster files that have been loaded. If you pay attention, for each product we are loading the bands 2, 3, 4 and 8. So with simple math you can now know the number of products we are using. So 6. 6 products and 4 bands per product. Okay, so once we have the data in R, let's start to do something. And of course, the first thing you want to do, or one of the first things you want to do, is maybe to visualize the product, to see it. So that's what I'm going to show you now. So in this cell, basically what I'm doing is, first of all, setting some layout parameters. This is Jupyter Lab specific, so nothing very important here. So what you want to do, first of all, is to create a stack. So you might be already familiar with what a raster stack is. It's basically we are putting together raster layers that are individual. We are, let's say, stacking them on top of each other. And the raster stack structure is very common in R and other programming languages. They might be called different, but it is very important because most of the algorithms many functions in R are designed to work with stack as input. That's a structure that helps you to manipulate the data and to index them, etc. So the first thing we're going to do is to convert our list of raster layers that we have created before into a raster stack, and I'm going to save that into a variable called s2 stack. So nothing very surprising. Once I have this, I can now do a plot. I can visualize that, and I'm going to use a specific function from the raster package that is called plot RGB. This is very convenient because the function already knows that I have a multi-layer stack. So let's say a multi-layer raster where each layer is a band, and I just need to say, okay, here's my stack of layers, of rasters, and you only need to specify in which layer you have the red, the green, and the blue band. So since I am importing the files in the order 2, 3, 4, 8, we know that the blue band, which is number 2, is in the index number 1. The band green, which is the 3 in Sentinel-2, is in position number 2 in my list, and the red band, which is the number 4 in Sentinel-2, is in position number 3. I can confirm that by, for example, opening here the band in index 1. We can see that it is here the band number 2. And of course, if I go to index number 2, well, then I get the band number 3, and so on. By the way, if you are coming from Python and you are new to R, the R indexing does not start at 0 but at 1, so that's something you want to know as soon as possible. If I write 0, it's nothing. Okay, so we were saying that we wanted to plot an RGB, so we give the stack, we specify the index for the red, green, and blue channels, and then basically we are setting the max values, so the range of values for our pixels. We are saying, okay, they go from 0 to the maximum value of a band of reference, which in this case I have used the Sentinel-2, I have used the layer number 2, but you can use any other. This is just to help the function distribute the colors from one value of a pixel, from a minimum value to a maximum value. The minimum is usually 0, so you don't need to specify that. And finally, we are setting the stretch parameter, which in this case is going to be histogram or hist. Let's plot this, and we will talk about this parameter later on. So I'm just going to run this, and here we get the output. So what we are visualizing is a true color and false color composition of one of the products we are going to be analyzing today. You can see that the first plot, the one on the left, was created with this specific line where we specified that the red channel was on 3, 2, and 1. And then what we have done is we have added the study area, the bounding box of the study area with this yellow rectangle here, and we have done so with this other line where we say plot the study area. We want to specify a border color, in this case yellow, a width for the line, so 5, and the key parameter here is add true. Add true in R means that we want to add this specific plot to a previously created plot. So for example, well, not for example, but actually this one. So if you do not plot anything before the add true, it's going to fail because it doesn't know where to plot it. So first of all, you need to visualize something, then another thing, and with the add the true parameter, you can stack the visualization together. As I was saying, the LWD is just the width of the line, so you can change that and play with the visualization. For example, let's have a look. If I put 10, you see now that the lines are much more visible. So as you can see, R is not by default, let's say, a visualization tool. Definitely, it's more to analyze the data, run your analysis, and export it and maybe finalize the layout maybe in a GIS software or something like that. But definitely you can play with it, and there is a lot of parameters that you can set, and this is gonna help you to automatize the creation of the layouts that you want. So I was saying, well, basically here we do the same to create the font scroll composition. The only difference is that now we are saying that in the red channel we want to pass the index number 4, which is the near infrared. We move the red channel into the red band into the green channel, and the green band into the blue channel. So basic operations. So I was saying before that I wanted to comment a little bit more about the stretch hist. So basically what we are doing here is telling R the way we want the colors to be distributed along our data. So the values of our raster go from 0 to the maximum value of this specific raster that is taken as reference, and we want to assign the colors to these pixels using a histogram stretch or clip, right? So we are following the data distribution to put the minimum and maximum colors related to the histogram. Again, this is something very common when doing visualization of data. However, this is something you can change in R, and it's going to give you a very different output. The alternative to this is to put the parameter lin, and basically this is going to change the way the colors are assigned to the pixel values. It's just going to follow a linear distribution, and as you can see, the visualization gets heavily affected, or gets affected somehow. Up to you, whatever you prefer. Okay, so this is our product. This is a true and false visualization of our products with the region of interest added. And remember, before we just locate it on a map so that you can locate it in the world. Okay, so the next thing we are going to do is to start processing our data, and the first thing someone might want to do is to crop it, right? It doesn't make sense to carry on with this large data set and heavy data set throughout the different processing steps if you are only interested in this specific region. So I would recommend you that you crop your data as soon as possible, so that you only keep whatever you want, and you save some memory space, and definitely you speed up your analysis. So cropping or subsetting, clipping is one of the things you will do first. And in R, this is very, very easy. So how to do it? Well, first of all, again, I'm setting some layout parameters in Jupyter Lab, so nothing in particular here. And well, how to crop a raster in R? Well, that is by using the crop function of the raster package in R. So as you can see, very explanatory by itself. So what I'm doing here is I'm creating a new variable called Sentinel-2 stack crop, and I'm saying, okay, in this variable I want to save the output of the crop function of the raster package, and this function needs as input the raster files that have to be cropped, in this case the Sentinel-2 stack. Remember, this Sentinel-2 stack is what we have created here before plotting this, and after creating the list of files with the previous cell, right? So this one. Okay, so the input is the Sentinel-2 stack, and basically we want to crop it using as reference a study area. The study area is pointing to the shapefile of our study area, which the key thing here is that it must have the same CRS, so the same projection, because if not, obviously, and this is common for geospatial analysis, they're not going to fit in the space, let's say, and it's going to crash. Okay, so let's run this. Again, after the crop, we are just again going to plot the true color and false color. Okay, so right after the cell has been executed, we get our outputs, and again we see the result of that. So nothing very surprising, we just crop our images to the size of our study area. As you can see now, I'm not adding to the plot the let's say the polygon by itself, because it's basically the same as the extent of this product. Well, something to point out and to visualize again is this difference in color representation that we can have if we use the stretch method of histogram or stretch equal lin. So let's change one of them. For example, actually what I'm going to do is create a new cell to avoid cropping the products again, which is this kind of a time-consuming step, not allowed a few minutes, but it doesn't make sense to do it again. So I'm just going to copy-paste this. I'm going to change the parameter to linear, and I'm just going to execute the visualization of this. Okay, so here we get the output, and as you can see, the difference in the way the colors are stretched is much more noticeable here. Well, this is just the consequence of using a histogram stretch or not, right? In this case, the colors are concentrated in the range of values that are more common, and here we are just going linearly from 0 to the maximum value and putting one color in every step, and the contrast change, etc. Something you might want to do when working in R is to check the help of a specific function. So for example, here I was saying that to do the crop we were using the crop function, but maybe you don't know what are the parameters or what are the many other arguments that this function can take, etc. This is something I have, that you will end up doing when working with R or the other programming languages a lot. One of the nice features of R is that you can access the documentation of a specific function directly, and if you are a user of RStudio, you know already where to find it. There is a dedicated tab for that. In Jupyter Notebook, you can just follow the same syntax. We can write the name, we can write the question mark icon and followed by the name of the function. If you do so, well, the documentation of the function is going to pop up, and basically here you can access all the information, right? So for example, the crop function belonging to the raster package, description, and basically all the information you might want to know. I think this is something very helpful. I think also the fact of working in Jupyter and having it display in this way, and I think it's very nice, but obviously this is information that you can also find on the internet if you just look for the documentation online. And by the way, something to point out as well is that it can happen to you in R that, especially if you start to work with a lot of packages, it can happen that sometimes one package has a specific function that has the same name as in another package. And this can cause confusion and will cause confusion to your analysis because let's say we have two packages with a function that is named the same, so crop. How can I specify that I want to use the crop function of the raster package in particular and not the crop function of another package? Well, this in R is done by writing the name of the package before the function, followed by this notation here. So basically here we are saying go to the raster package and use that and not to any other package. By default, this is purely an R thing. The way R works is that when looking for the crop function, it will check for it following the order in which the packages have been loaded. So if the first package that was loaded was raster, then it will take the crop function of raster. If you want to use the function of another package but with the same name, either you load it before or you just specify in your scripts this, which I think is much better. Okay, just a side note on this. Okay, so let's continue with our exercise. We have cropped our images, we have visualized the output of this, and now we can continue by deriving the NDVI index. So I assume you are all familiar with the NDVI index, so I will not go into the description of this, but basically, and for those that might be new to it, the NDVI, or the normalized difference vegetation index, takes advantage of the jump there is in reflectance for vegetation between the red part of the spectrum and the near-infrared. Yeah, but I don't want to go into why this happens. It is related definitely with the structure of the leaves, and we go into chemistry. but basically the idea is that there is a jump between the amount of light that is reflected and absorbed in the near infrared and red, and by normalizing this difference we can create an index that is going to tell us where we can find visitation. It's going to be an index that you can relate to that. Obviously it's a very well-known index in Earth observation, so something very basic. So how can you derive it in R? Well, there are definitely a lot of ways, and the one I'm going to show you today is one that incorporates a little trick when working with a lot of products for which you want to derive the index. There are dedicated functions to derive NDVI. There are many ways you can do it, and this is just one of them. So let's follow the logic. What we have here is 6 products, 6 Sentinel-2 images, and for each of them we want to derive the NDVI index so that we get the temporal evolution of that. Definitely we can go one by one and do it. However, the idea, right, of working with a programming language is somehow to automatize our analysis and well, save time, you know, things like that. So since we have 6 products, you can assume that what we want is 6 NDVIs, and this is more or less something that you want to store in a list in R, right? So what I'm doing first of all is creating a variable called NDVI, and this variable is going to be a list that so far I don't know how I'm going to populate it, but it's going to be a list. Each element of the list will be the NDVI of each of my products. So what I'm going to do next is to start a for loop. So basically starting here, I'm just going to have it like that. Okay, so I'm saying for I in 1 to the length of S2 divided by 4. So for every element that goes from 1 to the length of Sentinel-2. So remember, Sentinel-2 is the variable that contains the list of rasters. So if I just write here length S2 and I run this, it gives me 24, right? You remember 4 bands, 2, 3, 4, and 8 times 6 products, 24. Of course, if I divide that by 4, it's going to give me the number of products I have, 6, right? So I'm saying for I in 1 to 6, and this means the number of products I have, I want to do a specific operation. I'm going to say that the first element of my list, so NDVI double square bracket I, in R, the double square is used to access a specific element in a list, right? So if I just write Sentinel-2, for example, like this, I'm accessing this specific element. I'm accessing this element on this list so that I can start to operate with it, right? So if I just use 1, I'm not at that level, so I'm just, let's say, simply speaking, visualizing the first element, but I'm not within it. So that's why we use double quotation. So I'm saying for NDVI position I, and I goes from 1 to 6. So let's say we are in the first iteration, so I equals 1. So for the first element of my NDVI list, I want to overlay, and overlay is basically a function in R and coming from the raster package that is going to allow me to do algebra with the rasters. So I'm going to say Sentinel-2 stack crop. So this is the variable that is saving my crop data. And as you can see here, I'm using double square brackets. So I'm opening here the double square brackets and I'm closing them there. And basically here I see this little trick. This is the key part of the line. I'm saying I minus 1, then times 4 plus 3. So what's happening here? Well, let's imagine, well, let's not imagine, but in the first iteration of the for loop, I is going to be 1. In the second iteration, I is going to be 2, 3, 4, 5, 6, right? So when I is 1, let's do the math together. 1 minus 1 is 0, times 4 is 0, plus 3, 3. So what I'm saying is the NDVI in position 1 has to take the Sentinel-2 stack crop in position number 3, and if we check that, the position number 3 here, this is band number 4, and then I have to take the if we continue with the sequence here, we say, okay, take the number 3, which is the band number 4, near infrared, and then take another band, which is I minus 1 times 4 plus 4. So 1 minus 1, 0, times 4, 0, plus 4, 4. If I go to number 4, what I see here is that we are taking band number 8. So as you can see, we are taking the two bands that are needed to derive NDVI, right? The near infrared and the red. In Sentinel-2, the near infrared is stored in the band number 8 and the red in band number 4. Okay, so what I'm saying is just take these layers and then apply a function. So I'm saying here fun equal function, and I'm saying this function must have two parameters, x and y. These x and y are going to be coming from these layers that I have identified in advance, and I'm going to say, once you have these parameters, just do y minus x divided by y plus x. If you know NDVI, this is basically the formula of NDVI, right? Neo-infrared minus red divided by near-infrared plus red. So this is the little trick. So when I, in the first iteration of the for loop, when I is equal to 1, what I'm saying is go and take band number 4 of the first product. Pay attention here to the date, 2020-05-05. Then take the red band of the same date and do near-infrared minus red divided by near-infrared plus red. When I is equal to 2, let's do the math together. 2 minus 1, 1, times 4, 4, plus 3, 7. If I go to number 7, I can see that now I'm taking the band number 4, but this time of the 2020-06-04 product, so 1 month later. When I is equal to 2, in this case 2 minus 1, 1, times 4, 4, plus 4, 8. If I go to number 8, I see that we are taking the band number 8, so near infrared, again from the 2020-06-04. And then I apply the function, I create my NDVI, and I store it in my NDVI list. Of course, we can do the same for all. I think you got it. When I, let's say, for example, I is equal to 5. 5 minus 1, 4, times 4, 16, plus 3, 19. If I just go to 19, you see I'm taking the band number 4, so red band of this specific product, 2020-09-02. And if I just do one more, the 20, I'm taking the band number 8, and so on. So I think it's clear. So as you can see, this is a way of deriving NDVI. It just makes use of this little, I would say, algebra here, this little trick to iterate over the different raster products that I have in my list, and give back whatever you specify in this fun parameter, in this case, the function of NDVI. Okay, so once this is done, what we are going to do is to basically set the name of the result to something a little bit more meaningful than what we have here. So I'm just saying, okay, the name for each NDVI layer has to be NDVI underscore, and then followed by the sensing time. The sensing time, as you can see, it is specified here, but it's just together with other things that we don't want. So what I'm saying is, first of all, what I'm doing is splitting this string using the underscore icon. So I'm saying here in this piece of code, I'm saying take this string, so take the name of the products that you are using, and divide it in different elements and split it when you find an underscore. And once you do so, I want to look for a T, which is this fixed character that we can see it. And this is something that you will find in all the Sentinel-2 products. And once you find the T, split this again, and in that way we can isolate the sensing time only, and then just attach it to NDVI underscore, which I think in the end is going to produce a better name. So let's run this. And let's see the output. Well, it's doing all the math, it's doing everything. Remember, the NDVI is happening at the pixel level, so every pixel is going through this function, and we get the results back. So what we get is a list, and we know that because we created here, but also if you are familiar with R, this type of indexing is, you know already, it's a list. The list has 6 elements, so that makes sense because we have 6 products. Each element is a raster layer, so that's good. The dimensions in a number of rows and columns, this corresponds to our study area, that's good. Resolution 10 by 10 meter, which is keeping the original resolution of our bands, great. The CRS is still the same as in the original data, so UTM zone 11. The source, in this case memory, means that this specific variable is stored in our RAM memory of our virtual machine. So this is not something that exists in our file. So if I close this, I'm going to lose this calculation. Then we see the names. So you can see NDVI underscore the date. So this is basically what we were doing here that I just explained. And then the values go from minimum and maximum from minus 0.99 to almost, so from almost -1 to almost 1, which is totally fine because if, well, it's a normalized index, NDVI, it's part of the name, and that's why we have the values normalized from -1 to 1. Okay, so we have our NDVI calculated. Again, we are not visualizing it directly, we are just seeing this metadata information, which is great, but of course we want to see it. So let's go down, and now let's set the layout. So here for the layout, I'm using a specific function that belongs to the raster vis package, and this function is called level plot. To visualize raster data in R, definitely there are a lot of ways to do it and different options, different packages. I just think the level plot function from raster vis is very nice, but you can follow your way. Okay, so first of all, I'm setting again some layout parameters in Jupyter Lab. So this is, I mean, it's specific from Jupyter, but basically it's telling me the dimensions of the figure I want to create. Then what I'm going to do is create some breaks. Well, I'm creating this variable called breaks, and this is just creating a vector of numbers that go from -1 to 1. Those are, let's say, the steps I'm going to use to assign the colors in my NDVI. After that, I'm just going to pick a color palette in R. In this case, I'm using the red, yellow, green. You can change that to whatever you want. And well, basically, once this is done, I'm saying level plot my NDVIs. And as you can see, as input, I'm passing a function. So I'm saying stack NDVI. So instead of stacking NDVI before and then passing that into level plot, I'm just doing it at the same function, which is also fine. Okay, so let's run this. And later on, I will comment the other part of the plot. Okay, so here we have it. Here we can see the visualization. So the top part of each figure, we can see the name of this specific layer. So NDVI 2020-05-05. Then 1 month later, we see the same area, the NDVI in this case of June the 4th, then July the 4th, August the 3rd, September the 2nd, and October the 2nd. So more or less 1 month time. Okay, so things to point out. Well, basically, as you know, NDVI vegetation, so the greener it is, the more active, let's say, the vegetation is. So red and yellowish colors are low NDVI, meaning low vegetation or low active vegetation. And the greener the color, the more active, the more green the vegetation is, right? As you can see on every of those plots, we can see these little blue points or blue marks. Basically, what I've done is that I have added to this NDVI plot the location of the points I'm going to use as reference to extract a specific NDVI value and then plot the temporal series. So the final objective of the exercise is basically to go to this specific point, give me the pixel value, then the same pixel but in this layer, and so on, and just plot a line out of that and see how it changes. We're gonna do this for 4 points over our study area, and the way I have added these points to my plot is again by using the level plot syntax. So I'm just gonna pass this to another line, and the way this works is that first of all we define the first plot that we want to create, in this case the NDVI plot. I just explained before, and now instead of doing the add equal true that I was showing here, if you remember, so if I go up, in this case I was adding this this polygon by using again the plot function and then passing the parameter add true, right? Well, in this case we were using the basic plot function of R. In this other case we are using again the raster.vis package, and this has its own syntax, which I think it's also very convenient and easy to understand. So we are saying the first layer of our plot is whatever this is, so NDVI, then we're saying plus, and then now we want to pass some points. So I say layer, SP points, points underscore SA. Points underscore SA, if you remember well, is the points we loaded at the very beginning. So if you remember when we were loading the auxiliary data, we were loading this shapefile, and that shapefile is basically those 4 points. Okay, so I'm saying load these points and then PCH call and BG. This is basically the parameters for the representation for the visualization of those points, right? So PCH is just so this number is an index for the icon that is being used. 69 is an index for this specific blue color. The background here is not showing up, and sex and low and the LWD is just for the size and width of the line. So basically visualization. I am pointing this out just to show you that even if R, let's say, is not the final tool to create the outputs, definitely has a lot of options, and if you know them all and if you know how to play with it, you can definitely automatize the creation of plots. Part of definitely that analysis is create visualizations to actually show what you have done. Okay, so you can do advanced graphics, let's say, with R as well. Okay, so here we see the evolution, and well, definitely if you pay attention, I mean, if you follow the trend a little bit, early in May was kind of green, most of the fields, and slowly towards the summer, they are most of them going into the yellow color, so note that active, and mid-summer some are still very green. Definitely this again is an irrigated area, and local knowledge of your study area is always going to help. So definitely there's some irrigation happening here, and well, September, October, etc. Okay, so if that is a first result of our analysis. However, we want to see this evolution, we want to see this change in the value, so we are gonna actually do what we have said, extract these pixel values. So to do so, we are gonna use again the lapply function. Again, this family of functions that is used to pass a list and a specific function. So I'm going to say, okay, to my NDVI layers, I want to apply a specific function that I'm going to specify right after this. So parameter NDVI, I'm going to say extract, that's the key function. The extract function from the raster package requires a raster as input, NDVI, or let's say the parameter of this function that is coming from this input here. So a raster, a location, so where does this needs to happen, so at the location of these points, and then basically we are saying some methods to specify the way that the data is extracted. Again, remember, if you don't understand what method is, bilinear, etc., remember you can always do like this, question mark, raster, 2 points, extract, and check the description. And for example, if we go down and we go to methods, let's see if I find it here. Here, it's telling you either, so it's a character, so you have to pass string, simple, or bilinear. And well, basically, if bilinear, the return values are interpolated from the values of the 4 nearest raster cells. If it's simple, then it's most likely gonna take the value of the exact pixel where it falls. So I'm using the option bilinear because I think it's a good way of taking the neighboring pixels around. Obviously, if you are using, for example, GPS location, if you went to the field and you know, okay, that's your exact location where you want to sample, then use method simple. But if you know, if you are not very sure and you want to take a little bit of context because maybe you know that pixel was affected by something in particular, well, I think it's a nice feature of the extract function that I wanted to show you. Okay, so method bilinear and then df equal true. df equal true meaning that the result of this is gonna be shown as a data frame. Data frame is something very common in R. It's a data structure very, very common. It's a table basically, simply put. Okay, so we run it and we are now visualizing the first element. So you can see it here. And remember, since we are using lapply, the output of this is a list. In this case, a list of data frames. If I just remove the index here, we can see the list. So a first data frame, second element, a second data frame, and so on and so on. So let's go to the first one, just for the demo. So we see the data frame, we see the name, NDVI 2020-0505. We see the data type, so that's double precision, this DBL. That's what it means. So it's telling us we have a number here with double precision. And the first column is ID, so 1, 2, 3, 4, and the second column is the NDVI, and is the value by itself, right? So 0.95 and so on. So what is that 1, 2, 3, 4? Well, obviously the points 1, 2, 3, 4. Which is the order? I mean, is this one or is this one, etc., etc.? Well, definitely this is something that when you play with the data, most of the times you will know, right, if you have created or not the points. This 1, 2, 3, 4 is making reference to the way these points were loaded into R. If we go to points.sa and we go to the chords, so this is just, so maybe if you don't know, I can show this. If you, once you load a shapefile, you can access different methods and, for example, the bounding box, the data, the projection of this shapefile, etc. And one of the arguments is coordinates, right? So this is telling us in UTM coordinates X and Y, the location of these points. So this is point number 1. Those are the coordinates of point number 1. And basically, if you know, if we plot, for example, here the coordinates, we could know which one it is. Again, those are little details that are very important, but when you work with the data, when you create your points of reference, etc., it's something that you know, but definitely there are ways to figure it out. Okay, so we get these data frames, but obviously, you know, this is, I mean, I see that point number 1 is going from 0.95, then in a month later it goes to 94, then to 89 and so on. But obviously this is not, you know, the best visualization you can do. So let's move on. So what we are going to do is arrange this data frame a little bit so that we can actually plot a line a little bit better. So what we are going to do first of all is to combine these data frames into a single one. And for that I'm going to use the function cbind. And I'm going to create a single data frame for everything. And then what I'm going to do is to remove some duplicates. So let me comment this line with this hashtag icon so that we see the effect of this afterwards. So let's run this. And well, now we see all the data frames that were individual elements in a list are now combined. But now we see, you know, okay, great, but it seems there's something repeating the ID column, right? This is, I mean, fine, but I don't need to be refreshed every time with the ID. I know the row number 1 is point number 1, and I don't need that. Well, here you are seeing something very common when working with data in a programming environment, and when working with data in general, you will have to go through data cleaning and data preparation. This is something, it's part of the work, it's part of the job, and most of the times it can be a big part of the job. So in this case, what we are going to do is say, okay, let's get rid of these repetitions. We don't want them, and for that I'm just saying, okay, in my data frame I want all the columns, and I want to avoid the duplicates. So I'm using this exclamation mark to say, okay, if the duplicate is true, then remove it, and check the column names for that operation. So if we run that, now we see the output, and we have a clean data frame. So great, now we are close. Now it's easier to see the evolution of the points, but of course, you know what we want. We want a plot, we want a graphic, and it's going to be easier for everybody, so let's do so. So here what we can see is that we have a data structure where we have, for one sample, in one row we have different values, right? So this sample in row number 1 has this value, then this value, this value. This is something that doesn't follow, let's say, the preferred data structure for visualization in R. So here we are going a little bit more deep into the way different packages in R works. I'm talking about the structure that is required by the tidyverse or tidyr series of packages in R. Those are packages where which functions expect per row one sample. So in here, instead, as I said, we have different values for one sample in the same row, and the idea is to have in one row one sample, one value. So what we need to do is to let's say stretch this data frame, duplicate some values so that we have that data structure. Let me show you what I mean, and it's going to be easier to understand. So what I have done here is to use the gather function of the tidyr package that we have loaded, and basically we are saying, okay, take this data frame here, so this one, create the columns date and value, and gather it. So what we have here is that for per row, so in one row we have one variable, one value, and this is key to this is something that you need to understand when working with this type of packages like ggplot2 or ggplot. They all rely on this data structure: one row, one sample, one value. That's why in this case we have, instead of having the columns, the dates, now we have a column called date, and then you see it's repeating. So 2020 05 05 4 times, and for each of these we get one value. So again, this falls into this section of data preparation, data cleaning, data management. It's part of analyzing data with R or with any other programming language. It's part of the job, and as I said, usually takes a big part of the time you will dedicate to analyze your data. Okay, so we can see the data rearranged here, and now basically we can just plot it, and for that I'm going to use ggplot. It's again a very well-known library to create graphics. I'm going to pass a data frame as input. I'm saying the axes are the column date and value. I want to group them by ID, so this number 1 is the same, goes together with this number 1 and with this one, etc. And I want to link the colors to the IDs, right? So the number 2 in ID must have the same color as this other sample, and as this other sample, they are together, you know. Okay, then I want to create a line between them, between each record, and then I want to, on the line, I want to plot the points so that I can see it. As you can see, I have commented this line here, and let's run this and I will comment it later. Oh, sorry, since I commented, it's not showing. I just need to do this. Okay, so here we get the plot, and as you can see, it's not very nice, obviously, because I have played with the way the Jupyter notebook is displaying the outputs. And I'm showing you this to show you what happens with when you deal with data. I mean, obviously in this type of exercises I've run already the code and I fixed the issues, but this is something that can happen to you, and you need to know how to approach it. What's happening here is that we are getting the plot very big since I have been playing with the way Jupyter is delivering the outputs. If you remember, in my previous plots, I've been using this option here to set the width and height of the plots, and this is affecting the default values that Jupyter is using to plot the outputs. So in this cell, since I didn't specify anything, it's using the last thing that was set, and that's why I see the graph like that. Obviously, there are ways to change that manually, and ggplot has a lot of ways to custom your graphs. However, in here, I want to show you something that you might not be aware. Maybe if you're intermediate users of R, this can be of help, and definitely if you are beginners as well, is to create an interactive plot. So it would be nice, for example, to go along this line and know this value, and interact with the graph by itself. For that, we're going to be using the Plotly library, which is available in R, and it's a Python library. Mainly you will see a lot of examples in Python, but it has come to R, and it is very easy to use. Basically, we can create a ggplot graph and then embed it into a Plotly visualization. Let me just run it and show it to you. Okay, so here it is. So as you can see now, we get a better visualization. I'm setting here a height, but Plotly is by default arranging everything. It knows how to set up it has some default values, and is setting this graph for me. So we can see the plot, we can see the different colors. I'm just putting the default ones, the different lines. The thing you want to check when you do these kind of things is that the color assignment has been the proper one, the group of the data here that we set is the correct one. So the one goes with the ones, the twos go with number 2, and so on. And well, as I told you, this is a graph, an interactive graph. So the good thing is that we can use our mouse to check the value at a specific location. Definitely you can do this with a non-interactive graph, but I would say it's a little bit more less friendly, I would say. So we get the date, the value, so the information on the axis, the ID, etc. Other nice things is that you can zoom. This is definitely not a very it's not a very advanced graph, so we have just few lines, but you can imagine whenever you do a heavy graph with a lot of lines, the fact of being able to zoom and pan around the graph, I think it's very, very nice, and I think this is the kind of thing that makes your analysis look a little bit better, a little bit more professional. You can move around, and I think it's nice. Maybe you didn't know and just wanted to share with you. So auto scale, and well, basically here on top you can see different options. One of the good things as well is that you can, if I'm not wrong, yeah, exactly, you can download this plot as PNG. So basically you can click here, and this is gonna trigger a internet download with the graph. So I have downloaded here, and basically this is now a PNG in my virtual machine, and this is the file that I can now share with others. It's here, share with others and put in my reports or whatever you do. Okay, so I'm gonna finish here the exercise. Just gonna go back to my slides, and we'll finish the session. Okay, so basically, and to finish this session, I just wanted to share with you some conclusions. So with the massive volume of data being produced by the Sentinel satellites, the challenge in remote sensing in Earth observation is not anymore data availability, but rather storage and processing capacities. To solve this, there's also a knowledge gap, so how to use the data. So to solve this, RUS Copernicus is providing a free cloud computing environment, so virtual machines, where you will find a dedicated help desk with your experts to support you in your activities with Sentinel data, and as you know already, a dedicated training program. So I know it has been maybe a long webinar. We go through the different details of the R programming language. I went a little bit into the detail of the script. I hope for those of you that are beginners, this motivates you to continue your work with R, to continue learning this programming language. It has definitely a lot of potential, proven potential to help in your data analysis. For those that are intermediate and advanced users, I hope maybe you have learned some new details today. Maybe you are familiar with R, but not with Earth observation or with Sentinel in particular. So in general, I hope you have learned something new today. We are now going to move to the Q&A session. So I will just wrap up here this session, and I just ask you for a few minutes so that I can read through your questions, and we will be back live again with the Q&A session. So thank you very much again. I hope you have learned something new today. I appreciate you have been here today, and I hope to see you soon in another RUS Copernicus webinar. Bye.